In the previous part of this lecture, we had classified all cyclic groups. We saw they were completely classified by how large they are, by their order as a set. We also proved that infers that any two cyclic groups of the same order have to be isomorphic to each other. So being cyclic is very, very, very strong. I want to prove a few more things about being cyclic, which are important and will also lead us into future handouts. The first thing I want to point out is that being cyclic is an important example of what's called an invariant property of groups. And we're going to get into invariance in 1 or 2 lectures from now, and it'll be one of the last things we do this semester. And being an invariant property means that property is preserved by isomorphism type. In other words, any group isomorphic to a cyclic group itself has to be cyclic. And this is an important idea, and I want to prove that because, again, being cyclic is a good example of an invariant because it's actually not too hard to understand, and it's not too hard to prove that it is indeed an invariant. Let's prove it. Suppose that G is a cyclic group and that G is isomorphic to L. I claim that L must also be cyclic, and this is what it means to say that being cyclic is an invariant property. Okay, so let's prove this. So by assumption, there's an isomorphism from G to L, right? By assumption, so call it alpha. Alpha goes from G to L, and it's an isomorphism. Now, since G is cyclic, there must be an element that generates it, all right? And so I claim that if you had a generator for G, call it A, if you simply watch where A goes under your isomorphism alpha, so map A into L and call the result B, that thing will have to generate L, and that proves that L is cyclic. In other words, an isomorphism must map a generator of G into a generator of L. Okay, but I got to prove that. So I claim that B generates L. Well, to show that B generates L, I take an arbitrary element of L, and my job is to show that arbitrary element of L is expressible as a power of B. So let's do it. You take your element from L and realize that alpha is onto because it's an isomorphism. So since alpha is onto, you have y in here. There must be somebody in here, call it x, that hits it. So there must be an element x in G with alpha x equals y. That's just the definition of being onto. But G is cyclic generated by A, so that means that everybody in G, namely x itself, must be expressible as a power of A, right? So x is writable as a to the k for some power A. But now just do the math and use the fact that alpha is a homomorphism. So y, remember, is alpha of x, but x is a to the k, so that's alpha of a to the k. But that's alpha of A to the k because alpha is a homomorphism, but alpha of A is B, right? Alpha of A is B, so that's B to the k. So look, y is B to the k. So every element of L is a power of B. That means that L is generated by B, so it must be cyclic. And that's the proof, right? And so that gives us an immediate corollary, which is suppose that G is cyclic. Then how do you know if a group L is isomorphic to it? Well, that happens if and only if L itself is cyclic and of the same size. And that's just this theorem with everything else we've done before this. Okay? So what I really wanted to get to here is this amazing fact that we can now prove in a few short sentences, which is we can finally use everything that we know so far to actually classify groups of prime order. So we already classified all cyclic groups, and I claim that we can now use that and classify all groups of prime order. And the proof is, look how short it is. This is now very easy. So here's the classification of groups of prime order. Let G be a group of order P, where P is a prime. Then G has to be isomorphic to Z mod P, and there are no other options. In other words, there is exactly one isomorphism type among groups of order P, and the one model is Z mod P. And the proof is easy. If you look at our Lagrange's theorem handout, we proved that a group of prime order has to be cyclic. We proved that already. That's just an easy application of Lagrange. So a group of prime order must be cyclic. So if G is a group of order P where P is a prime, it must be cyclic. But cyclic groups are unique up to isomorphism type given their order. So since G is cyclic order P, it has to be isomorphic to ZP, and you're done. So therefore, any group of order P must be isomorphic to Z mod P, and that's the only option. So there's only one isomorphism type. Okay? So we're going to look at some more classification problems coming up, and then we're going to come back to this idea of looking at invariant properties and see what we can use those for to prove good theorems. But that's coming up.